folks. JLand Bio here again. We are going to be diving into our solutions unit, the fourth of 6 videos, and we are going to focus on what is known as solution stoichiometry. I know, it just keeps coming back. You just can't get rid of it. But yes, we are going to focus on solution stoichiometry today. Really not that hard. The only difference here is that we need to consider that molarity can be used as a conversion factor between moles and liters of something. So we're going to dive on in and get started. Hopefully by the end of this video you will be able to understand that molarity can be used as a conversion factor. That sounds familiar. And to be able to calculate a variety of different variables using solution stoichiometry. There are no vocabulary terms in this particular unit. Not a, zilch, zero, none. Get excited, because we're about ready to dive into the wonderful world of solution stoic. I can't think of really anything creative here, so just put a big smiley face, because I know how much you guys absolutely love stoichiometry. You've been ranting and raving about it since we started. What you need to keep in mind for this is that molarity is the relationship between the amount of moles of solute and the volume of a solution, so we can use it as a conversion factor. That's all there is to this. All the rest of the rules are exactly the same. Let's do some practice problems. All right, here we go. How many milliliters of 0.280 molar barium nitrate are required to react completely with 25 milliliters of 0.350 molar aluminum sulfate? Oh, we are doing stoichiometry. The very first thing with stoichiometry is to always, always, always write a balanced chemical equation. So we're going to do that first. I'm going to do that up here. So we are reacting barium nitrate. So BaNO3. And we're reacting that with aluminum sulfate. So it's AlSO4. We're going to produce, if we take a look at this, we know this is a double displacement reaction. So we're going to have BaSO4 and aluminum nitrate. Okay. Now before we do any of this, we need to make sure we wrote our formulas correctly. To do that, we need to look at the charges or oxidation numbers that we find on the periodic table. Ba is a +2, NO3 is a -1, so remember BaNO3, 2. Al +3, SO4 -2, so we need 2 there. SO4 is going to have a 3 downstairs. BaSO4 is +2 -2, we're good there. Al is a +3, NO3 is a -3, so we need to put 3. Sorry, Al is a +3. So we put a 3 down there. All right, now we get to go through and balance our equation. Toughest is going to be nitrates, because we've got 2 and 3, so we need to make those 6. So let's put a 2 here, and let's put a 3 here. Okay. And now we need to put a 3 in front of BaSO4, and we're done. So that equation is balanced. So now we can start making our stoichiometry. The question is asking for how many milliliters of barium nitrate. Okay, so that's what we're going to end with. So we're going to start with aluminum sulfate. I can't start with molarity because that's a ratio, that's moles per liter, but I can start with 25 milliliters. So we're going to start with that. So we got 25 milliliters Al to SO4. 3. Okay, so we get 25 milliliters to start. Milliliters on the bottom, the next step. Only thing I knowingly convert milliliters to is liters. Okay, there's 1,000 milliliters in a liter. Okay, so now we got liters. Remember that molarity is moles per liter, right? So I can use that as a conversion factor for aluminum sulfate. Moles per liter, so in this instance it's 0.350 moles for every 1 liter. Okay? Now I've got moles of aluminum sulfate on the bottom. Now I can convert that using the mole ratio, again a lot of stuff you're seeing here, to what I'm looking for, which is barium nitrate. I use the coefficients of my balanced chemical equation, so 1 and 3. Okay. Moles at the bottom. Again, taking a look at what I've got here. So moles. What do I convert moles into? Well, the question's asking for milliliters. I'm also given another molarity, right? So I can go moles to liters here as well. 1 for liters and 0.280. And then the very last step, which I'm not sure we're going to have enough room here, but it's not asking for liters, it's asking for milliliters. So 1 liter is 1,000 milliliters. So it's a lot of steps, but you walk through it just like any other stoichiometry problem that you have. So now all we do is we just plug in and solve. So we'll multiply across the top and divide by what's on the bottom. I take a look at my response here. I need 3 significant figures, so my answer is going to be 93.8 milliliters of barium nitrate. Okay, that's all there is to it. So again, the key thing here, make sure you have your balanced chemical equation and then take it one step at a time. And just remember that molarity can be used as a conversion factor between moles and liters. Many times you're going to have to do milliliters to liters to get through that. Also understand that your mole ratio is very important here. Let's make that the word of the video. We'll go mole ratio for that one. Okay, so mole ratio, again, word of the video here in practice problem number 1. I'm saying it like 9 times. That's the word of the video. Make sure you write it down. All right? Same type of problem we got going here in practice problem number 2. The question is asking for volume of 0.415 molar silver nitrate to react completely with 35 milliliters of 0.12 molar calcium bromide. So it is the same thing. We need to make sure we write our formula, our balanced chemical equation. Calcium bromide. Okay. Again, I did that a little bit faster. I would expect you guys, take your time, make sure you're writing everything correctly, know what numbers go where, make sure you look at the charges that are associated with the compounds before you move forward. All right. So again, we start with the same thing we looked at last time. So we're solving for silver nitrate. Okay. So we're going to start with 35 milliliters of calcium bromide. So again, same concept, 35. Okay, calcium bromide. Again, milliliters on the bottom of the next step. We're going to convert that to liters, just like we did last time. 1,000 milliliters in a liter. Liters, again, using the molarity as a conversion factor. It's 0.128 per liter. Okay, so we're going to go from moles of CaBr2, and we're going to change that and get it to moles of silver nitrate. And when you look at the coefficients of your balanced chemical equation, CaBr2 is a 1, AgNO3 is a 2. Moles, again, the question is asking for volume. Doesn't give us milliliters, so we'll just go to liters. That's fine. Again, if it doesn't give that to you, then, just think about what would probably be most useful. You could go milliliters, you could go liters. However you'd want to do that's fine. Okay, just make sure you give me what the question's asking for. And again, just plug your numbers in and solve. So our answer needs 3 significant figures again. So I could say 0.0216 liters of silver nitrate. Or again, if I wanted to convert that to milliliters, again, you just multiply by 1,000. So you'd have 21.6 milliliters. Okay. And just make sure you give me what the question's asking for. Plug your numbers in and solve. That's all you got to do. It's pretty straightforward. Let's do one more practice problem. Psych! That was the last problem. So, long story short, keep in mind that molarity can be used as a conversion factor between moles and liters of a substance. Keep in mind your stoichiometry rules and make sure you understand that molarity is that conversion factor that we're looking at.
So take a look at our learning targets. Hopefully we've met those. We're going to use solution stoichiometry a little more in depth. I just wanted to give you guys an introduction to it. We will talk to you next time. So have a great day, guys. We'll talk to you later. Bye-bye.